Welcome to Chapter 5, Introduction to Hypothesis Testing. In the Chapter 5 lecture video, we will talk about the 5 steps of hypothesis testing, one-tailed and two-tailed tests, and type 1 and type 2 errors. So first, let's talk about some research terms that we're going to be using. The first is hypothesis. A hypothesis is a prediction intended to be tested in a research study. It can be based on informal observation or based on theory. What is a theory? A theory is a set of principles that attempts to explain one or more facts, relationships, or events. A theory usually gives rise to various specific hypotheses that can be tested in research studies. So just to be clear, we don't test theories, we test hypotheses that are usually based on theories that had other hypotheses that were tested. Okay, so let's continue. So for today, we're going to be talking about a specific research study that is given as an example in our book. It's a completely fictional study, and our subject sample is very small, and so you'll see why it's fictional. But it's just to give you an idea of how we would do all of the steps in hypothesis testing. So let's start with some basic research data. During a 2-year study of when babies begin to walk, researchers wanted to study a new purified vitamin to see if it might help babies to start walking much earlier. So here's our hypothesis. A specialized purified vitamin will help babies start walking earlier than babies who don't take the specialized vitamin. We study a sample to make a conclusion about a population. And so this chart just kind of shows the general population statistics, and we'll go through that in a little bit more detail in just a few minutes, okay? Now, for this study, we have 2 populations. Population 1 are the babies who are receiving the specialized purified vitamin. Population 2 are babies in general, or babies who are not getting the vitamin, okay? So when you're thinking about your study, you always need to identify your populations. Now let's talk about just briefly the logic of hypothesis testing. How will we know our hypothesis is correct? Well, I'll tell you. You'll never know for sure if your hypothesis is completely correct. In fact, when we think about our theories based on hypotheses, it's one of the reasons why sometimes critics will come back and say, well, that's just a theory, it's not a fact. And that's true. We can't say that it's a fact. We can say that we have evidence to support our hypotheses that support our conclusions in support of our theory. So what we have to do is prove that any effect we see is not due to chance. So in order to do that, we look at 2 types of hypotheses. One is our research hypothesis, and this is the statement in hypothesis testing about the predicted relationship between the populations. Okay, and I'll go into this in a little bit more detail, but this one specifically for our test is the babies who take the vitamins are going to walk earlier than the babies who don't. That's our research hypothesis. And then we have what we call a null hypothesis. Null just means nothing. It doesn't work. The hypothesis didn't work, okay? And so we call this a null hypothesis, and I'll show you some things about the null hypothesis in just a few minutes. But it's a statement about a relationship between populations that is the opposite of the research hypothesis, okay? And so we're going to talk a lot about the null hypothesis in today's lecture. All right, so step 1 of hypothesis testing. Restate the question as a research hypothesis and a null hypothesis about the populations. So our research hypothesis, babies who take the purified vitamins, population 1, will walk earlier than babies in general, population 2. So I've kind of abbreviated this, that the mean age for walking, for starting to walk for population 1 will be less than the mean age for population 2 for babies who start to walk, okay? And so I've just kind of abbreviated this into kind of a mathematical formula. What about our null hypothesis? And I want you to take a look at the abbreviation that I've shown you here. I don't think our book uses this abbreviation, but this is the abbreviation I was taught. It's an H with a 0 subscripted like you would do H2O, only this is just HO, okay? Sometimes just called HO, and we're almost in that season of ho, 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 so you can think of this as the HO, okay? So this is the null hypothesis, or the HO or HO. Now the reason we call that this is that it's the hypothesis, H, and it's the null hypothesis, null meaning 0. Okay, so this is the hypothesis of 0 effect. And so this hypothesis for our research study says there is no difference in walking age between babies who take the purified vitamin and babies who do not take the purified vitamin. Okay, so these are our first, this is step 1. These are our 2 hypotheses. Okay, step 2, determine the characteristics of the comparison distribution. Now the comparison distribution is the general population, okay, babies in general. Now for this fictional study, our researchers have been studying babies in general for 2 years. They've been collecting data about babies, and they know that in general, babies start to walk on the average at 14 months old. So at 14 months old, here we have the mean. Here's our normal curve, right? And here we have the mean, and here we have our data right here. So this is the data that we've been collecting for 2 years. At 14 months old is the average time when babies will start to walk. 3 months before that is 1 standard deviation below. So babies who might start walking earlier, 1 standard deviation below, is 11 months, and then 2 standard deviations below is 8 months. On the other end, 17 months is 1 standard deviation above, and 20 months is 2 standard deviations above. So this is one of those situations where later walkers, which would be less successful in this case, would be the greater z-scores. So notice how we have the normal curve that we've been talking about in the last couple of chapters, and we have the z-scores and the age, which is the score that we are measuring in this study. Okay, so a couple of things I want you to notice. The comparison distribution, which is this distribution right here, is the distribution used in hypothesis testing. We are testing the hypothesis, and we are gathering information about the population before we even run our experiment, okay? And this represents the population distribution if the null hypothesis is true. If our vitamin doesn't work, this is what our experiment is going to look like, okay? So if the null hypothesis is true, then the mean age for walking for population 1, our special vitamin babies, will be equal to the mean age for walking of population 2, which is our comparison distribution. Okay, so now we have determined the characteristics of our comparison distribution. We know that the mean for the population is 14 and the standard deviation for the population is 3. All right, step 3. Determine the cutoff sample score. We want our experimental group to have a lower mean than the control group. So our experimental group is the group of babies that are going to get the vitamins, and the control group are the regular babies that are not getting the vitamins, okay? So let's say that our refined vitamin helps babies walk as early as 8 months old, which when we look at our normal curve, at 8 months old, it is a z-score of -2. And you guys remember from our analysis of the normal curve that a z-score of -2, remember the percentage that's under here is 2%. Okay, so now you're starting to understand why I had you guys doing that. So we had 50% from here and 34 and 34 here. Well, now you know why I had you guys looking all the way down here. If our babies that we study walk at 8 months old, then they are walking better than 2% of the general population, okay? So if our baby walks at this age, he is in the youngest 2% of the population, but is that young enough to be significant? So researchers, one of the things I want you to understand about the cutoff sample score, and this is something that students do ask about, because how do you decide, right? Well, researchers determine their own cutoff score, and we're going to be talking about that later on when we talk about the type 1 and type 2 errors that can be made. But when you determine as a researcher your cutoff score or your critical value, you get to make that choice, okay? But I will tell you that conventionally we usually use a 1% or 5% significance level, okay? And that's what we call it. It's a significance level. We could choose 2% right here and just say, hey, 8 months looks good, 2% significance level looks good. But generally speaking, when you start looking at research papers, when you're doing research in your career or in your other classes, you'll start seeing that the P or probability levels will be at 1 or 5%, sometimes at 0.001 or 0.1%. Okay, so let's look at this. Hypothesis testing step 3, how do we determine the cutoff sample score? Okay, where do we decide to reject the null? Remember that our goal is to reject the null hypothesis, the HO or H0, okay, or HO. Okay, so at the 5% significance level, if we're looking at our normal curve, remember, okay, I've marked it here in blue with the 1% mark and in green with the 5% mark. And it turns out that the z-score for 5% is negative 1.64, or 9 months in this case. And the z-score for 1% is 7 months, okay? Now, when a sample score is so extreme that researchers reject the null hypothesis, the result is said to be statistically significant. So if we choose the 5% significance level, or P is less than 0.05, remember that when you write it as a decimal, 0.05 is the same as 5%. So if we say that we're going to use the 5% significance level, then if our babies walk at less than 9 months old, then we're confident that it's because of the vitamin. But there is still a 5% chance that it's due to chance. So what we're going to do, we're going to be even more conservative, and we're going to choose the 1% significance level. And we want to say, we want to make sure our vitamin is effective at helping babies learn to walk earlier. This is a safe vitamin that's already been determined, but we want to see if it helps babies walk earlier. So we're going to test it at 1%, which is 7 months. So our cutoff sample score is a z-score of negative 2.33, or the significance level of 1%, or P less than 0.01. Okay, so that's our step 3. Now, after step 3, we run the study and we wait. Now, first, we have to do all of our stuff, right? From Appendix E, do you guys remember? We had to select our babies. We have to get the parents to agree. We have to give them the vitamins, all of those kinds of things, okay? So for this example, since this is fictional, we chose 1 baby and we gave him the vitamins, and let's see what happens. And we're watching and we're observing. Not every day the parents are observing and they're reporting back to us, and we find out, let's see what happens. And we're in step 4 of hypothesis testing, and look at that. Determine your sample score on the comparison distribution. Our test subject starts walking at 5 months. Okay, here is the sample data. Our sample score X equals 5. Our population mean is still 14. Our population standard deviation is still 3. So we calculate our scores, z-score, and we get -3. Look at our baby walking. Here we go. Now we've determined our sample score on the we've gotten the z-score. Let's look at the comparison distribution. So we need to decide, we're going to put it on this normal curve. Okay, we've already seen that it's a -3, and those of you who've been paying attention and taking notes, I bet you're already seeing what we're seeing here. Step 5, it's the last step of hypothesis testing. You need to decide whether to accept or reject the null hypothesis. You're going to compare your sample z-score to the cutoff z-score, okay? So here we have our normal curve. Here we have our baby's z-score. Here we have our cutoff z-score. And what are we seeing? Okay. What is the probability that the experimental sample baby starting to walk at 5 months was due only to chance and not due to our vitamin? Well, it's less than 1%. Less than 1%. There's less than 1% chance that our baby was just by chance able to walk at 5 months old. What does this tell us about our null hypothesis? Do we accept or reject the null hypothesis? Reject. Isn't that great? This is one of the things where you can say honestly that rejection is good. If you're rejecting the null hypothesis, this is a good thing. Rejection is good when it's the null hypothesis. And this is something I remember from when I was in school. This was so much fun. Not this guy necessarily, but we did used to say this: if the P is low, then the hoe must go. Okay, and I know you guys are feeling this with me. I hope you're hearing the sense of humor going along with this, but it is one of the things that makes it fun to do statistics and to listen to these lectures. I hope you're getting the humor. Okay, so we reject our null hypothesis. Yay. All right, what does that mean? The implications. When you reject your null hypothesis, it means your results support your research hypothesis. It doesn't mean that you have proven your research hypothesis, okay? It just means that your results support your research hypothesis. Someone could come in and say, as a critic, and could say, well, you only had one subject, and that's true. That's not very good. You need more than that. Someone could say you need to run this more often. It could be that you were giving the baby something else besides the vitamin, so you had some kind of other factor. So rejecting the null hypothesis is certainly fantastic. We love to see that when we're doing our research, but it's not just like all the angels are singing in heaven because you rejected the null hypothesis, but it does mean you get to support your research hypothesis. Sometimes, however, we do find that we fail to reject the null hypothesis, and that is how we say it. We fail to reject the null hypothesis. It means our results are not extreme enough to reject the null hypothesis. We do not say that our results support the null hypothesis. Remember, the null hypothesis is almost like the enemy here. We don't want to support the null hypothesis. We're just failing to reject it, okay? All right. So what does significance mean, okay? A result can be statistically significant, but it doesn't mean that it's meaningful or important, okay? Statistical significance refers to the strength of the evidence that the effect is not zero. It doesn't mean that this vitamin is a miracle drug. So sometimes what happens is manufacturers will misinterpret or deliberately misinterpret statistical significance to equate that with meaningfulness or importance and tell you that something is amazingly effective simply because of its statistical significance. And so you need to be cautioned about that. Statistics can often be used as almost like a weapon, and people will use it to mislead other people. And so you have to watch out for that. I always tell my students, as critical thinkers, we need to be really aware of who is paying for the study and who is benefiting from the study. So it's not just what the results are, but you have to look at who is benefiting from it. So you can see if perhaps there might have been some malicious manipulation going on. But there are other things we want to look at too. So we're looking at all of these things. We want to look at a summary of how we test these things. So first, you restate your question into the two different types of hypotheses, research and null hypotheses about your populations. 2, determine the characteristics of your comparison distribution. 3, determine your cutoff sample score or your critical value on your comparison distribution where the null hypothesis should be rejected. 4, determine your sample score, and that's when you do your research and you compare it to your comparison distribution, and then decide whether or not you're going to reject the null hypothesis. Okay. Now, what if we have, in our case, we did have a directional hypothesis test, okay? And what do I mean by that? Our test was looking at a specific direction. We wanted to see that babies would walk earlier than the average baby, not later, okay? And so that means we were looking at a specific direction of the effect, okay? So in our specific test, we were looking at a one-tailed test that was specifically lower, okay? One-tailed tests can also be higher, okay? We might have a reading level that might be greater in students participating in a reading program, and so it would be flipped. Remember that in a normal curve, the tails are equivalent, okay? They're the same in both ends. So your z-score, where you would reject the null hypothesis at the 5% level, would be just the positive 1.645 down here, okay? So in a one-tailed test, you're only looking at one direction, and so your full 5% of your probability is going to be in the one tail, okay? To reject the null hypothesis, a sample score needs to be in the particular tail of the distribution. In this case, we're looking for it to be in the bottom 5% of the distribution, okay? So that is a directional hypothesis, and for a directional hypothesis, we use a one-tailed test. In a non-directional hypothesis, we use a two-tailed test, and this is a hypothesis that predicts the effect but does not specify whether the score will be high or low. So in this case, the null hypothesis, or HO, says there will be no change in either direction, okay? And so we're looking for, we want it to be either higher or lower. We just want there to be a difference. And I can't think of one off the top of my head. I'm sure one will come to me briefly. But for right now, we're still looking at a probability of a 5% significance level. But we split the significance level between the higher and the lower scores. So now our cutoff scores are split. So it's our probability of 0.05 is now 0.025 and 0.025. So we have negative 1.96 for the z-score and positive 1.96 for the z-score. We reject the null hypothesis if the sample score is either in the top 2.5% or in the bottom 2.5% of the comparison distribution. And we would know then that the chance of our score being down here or up here by chance is that low, okay? That it really is a 2.5% chance that it would be up here, or a 2.5% chance that it would be up here, but it's a 5% chance total for it to be at either end, okay? And since it's a non-directional hypothesis, we use a two-tailed test. You'll have some homework questions that ask that, and I'm not sure if it gives you specific analogies, but this is when you would do a two-tailed test. Okay, so this is one of those GIFs that I found that shows when you would reject or accept. So you reject the null hypothesis over here. This is when you have a two-tailed test and a one-tailed test. A one-tailed test is over here. The two-tailed test is right here. Sometimes a one-tailed test would be just down here, okay? I thought that was a fun GIF. Okay, so let's look specifically at the differences for the 0.05 or the 5% significance level cutoffs, and then we'll look at the 1% level. So this figure shows the cutoff scores for the 5% significance level for both one-tailed and two-tailed tests. Remember to flip the tail for a negative score on the one-tailed test. So the cutoff scores, and what I want you to see here is that these z-scores are set. Remember that table that you've been looking at in chapter 4 to find the z-scores and the percentages for those. The percentage for 5% is, and the z-score that goes with it is 1.64. You could memorize it if you wanted to, but now you know where it comes from, okay? The cutoff for the two-tailed test would be plus or minus 1.96. See? So the two-tailed test is these smaller parts of the tail because we're dividing the 5% significance into both tails, okay? So we have the two-tailed tests are both sides. The one-tailed test at 5% would be right here. So these are the three different cutoff scores for a 5% significance on the one-tailed and two-tailed tests. It's similar for the 1% significance. Of course, they're farther out though. So the cutoff for a one-tailed test is 2.33, and it would be flipped if it were a negative. And the cutoff for the two-tailed test is for 0.005 is a z-score of 2.58, positive or negative. So here it is negative, and here it is positive. So this is the 1% significance cutoff scores for the one and two-tailed tests. Okay. When do you use a one-tailed test then? Here we go. We'll summarize it right here. You use a one-tailed test when you have a clearly directional hypothesis, but if the sample score is extreme, but in the opposite direction, the null hypothesis cannot be rejected, okay? So if you were using a one-tailed test, but is clearly directional in your hypothesis, and it just so happens that your score goes the opposite direction, you fail to reject the null hypothesis. So when do you use a two-tailed test? When you have a clearly non-directional hypothesis. And what happens is, in situations like the first one, in the one-tailed test, if you have a score that's going the opposite direction, what if there's something going on that you just can't anticipate? Often researchers will use two-tailed tests even if the hypothesis is directional. Why would they do that? Because it is more conservative, because they're using a lower percentage level, and so they're being more cautious about being sure that their effect is not due to chance, okay? And so you could do a two-tailed test because remember, it will divide your probability in half. And so you would have half the chance of getting it correct, okay? All right, so let's talk about the decision errors that can be made when you are doing a hypothesis test. So let's say that, you know, there's some database out there that knows the actual reality of your hypothesis, okay? And remember, we're calling the null hypothesis HO. And in reality, the null hypothesis is true, that there is no difference between your research group, your experimental group, and the control group, okay? There's no difference at all. But you reject the null hypothesis, then you have made a type 1 error. If the null hypothesis is true and you accept or fail to reject the null hypothesis, then it is correct. You are correct. You have failed to accept, you failed to reject the null hypothesis. You've accepted it. You're like, all right, yep, our effect didn't work. Our vitamin didn't work. Our reading program didn't work. Back to the drawing board, okay? Now, what if our null hypothesis is actually false? What if our effect really does work? What if our vitamin does help babies to walk earlier? What if our cancer treatment does cure cancer? Okay, when we reject the null hypothesis in this situation, we are correct. But if we fail to reject the null hypothesis or we accept the null hypothesis, we make a type 2 error. And so I'm going to go through each of these decision errors separately so that you can see what each one is and how we might correct for that. Okay, so let's talk about it in detail. First, a type 1 error is when you reject the null hypothesis when the null hypothesis is true. It's a false positive, okay? We're saying, yay, we were right, and it's not right, okay? A type 2 error is concluding that there is no effect when there actually is an effect, and this is a false negative, okay? So we're like, oh, it's too bad our stuff didn't work when it really would have worked if we had just stuck with it. Okay, so let's talk about the differences between these two. A type 1 error is a very serious error. Theories, research programs, treatment programs, social programs are often based on conclusions of research studies. We need to be very cautious that we don't make type 1 errors. We do not want to say that our solution, whatever our research solution is effective when it's not, because a lot of money is going to be wasted, okay? A type 2 error with a very extreme significance level, there is a greater probability that you will not reject the null hypothesis when our research hypothesis is actually true. And so we might actually make a type 2 error just because we're trying to be really cautious. And so there's a balance here, and that's what I'm trying to show you, is that you need to make, there's a balance in making a type 1 or type 2 error. Okay. Type 1 error. To reduce the chance of making a type 1 error, researchers set very stringent significant levels, and they will do the P of less than 0.001 or 0.1%. To reduce the chance of making a type 2 error, researchers can set a very lenient significance level of, say, 0.1%, of 10% or 0.1, P less than 0.10, okay? So a 10% chance that it's due to chance. And you can see that it's much more lenient than the example given here in the type 1 error. So it's that balance back and forth, back and forth. How much are you willing to risk? Okay, that's what you're risking. The chance of making a type 1 error is the same as the significance level. Okay, if you decrease the probability of a type 1 error, you increase the probability of a type 2 error. And so there's a compromise that we make, and that's what I'm talking about earlier, where we use a standard significance level of either P less than 0.05 or 5% and P of less than 0.01 or 1%. I do still see sometimes that people will use P of less than 0.001, but it's not common. These are the common significance levels that you'll see people, especially when they are setting their cutoff scores. Okay, now we will jump up for joy if we reach much lower probabilities. And we'll get to those later in the semester when we're talking about how we can calculate actual p-values. Okay, so here we go. We sum this up. I found this online, of course. There's so many funny things online. So a type 1 error or a false positive is a man finding out from his doctor that he's pregnant. That's a false positive. And here's a type 2 error, a woman who is clearly pregnant and her doctor is saying, no, you're not pregnant. No, that's a false negative. She is clearly pregnant. Okay, so that's a type 2 error. Okay, so lastly, and I'll just talk about this briefly and I'll close out the rest of this and leave the slides up online so that you can go through this yourself. Like I mentioned earlier, our fictional study had only one subject. One baby took our vitamin from birth on and started walking at 5 months old. Amazing, amazing. And we can say for sure that our marketing team can say our vitamin is amazing and babies around the world should be using our vitamin, right? No, because we need to replicate this study. And replication of studies is necessary. It is vital. We need to evaluate the validity of research findings, okay? We replicate studies all the time. We use the same methods, we use the same types of participants, and we use the same statistical analyses to see if we get the same results. Replication studies are challenging and they are becoming more common because we need to find out more data. One of the things that I'm seeing much more commonly now, which is fantastic, is a lot of the classic studies, classical psychological studies that were done in the 50s, 60s, 70s, and even into the 80s were done mostly on college students. And back then, most of them were white men. And so we need to redo those studies because we can't draw a conclusion about the whole population if the subjects were only white men, especially white college men in a time when most people didn't get a chance to go to college. So we're redoing some of those studies. A lot of those studies are being redone on diverse populations. And I love when we find out that a lot of those classical studies are holding up, that it wasn't just white men. And I love it when we're finding out even more amazing things. And so the replication studies are really important. And one of the other things that you'll see, especially if you get more into this, are the meta-analyses that are going on. And that allows for you to analyze very systematically, looking at the data that other people have collected over, the last few decades in a certain topic on memory and cognition and learning and behaviorism and a whole bunch of other things. You can look at the studies that have been replicated or are similar, and you can see, you can compile them together and do a meta-analysis, and then it's like you have a study of 10,000 subjects instead of 100 studies with 100 subjects, and or 1,000 subjects. You can do the math. So it's just a really great way of looking at the data a lot more deeply and getting a lot more information. So I hope that this lecture helped. They got some other slides to go through with to help you look at these kinds of things in research articles and in a summary. But these slides will be posted on eCampus later tonight. I hope you have a great night. Bye.